In this video, we are going to be talking about elevator problems. And elevator problems are either a good way to teach or torture physics students, depending on your point of view. So, what we're going to do first is we're going to draw the elevator. And there's lots you can do with this. Like you can find the tension here. And the whole idea is to look at forces and how they interact. So instead of doing the tension, we're going to put a scale down here that'll measure the normal force. And then on top of that, we will place the little dude. And now that we have a little dude, we can ask him what his mass is. And he is going to tell us 80 kilograms. The next thing that we need to know is that our little dude is traveling upwards at a constant 3 meters per second. So this is a force problem, which means that the first thing that we need to do is to define our system. So we are going to define our system as the little dude sitting on the scale. So we're then going to start drawing our free body diagram. So we are now representing the little dude as a dot. And we've got force due to gravity, which is pulling the little dude down. And then we've got the normal force between the little dude and the scale. So that's the force normal right there. Now, we know that because it's traveling at a constant 3 meters per second, that these forces are going to be equal to each other. But let's use Newton's second law, so F equals ma, in order to really go ahead and prove that. And this funky looking E that's before the F is the Greek letter sigma, which stands for the sum of. So that's adding up all the forces to find the total force. So we got the normal force, that's going to be positive because it's going up. And next we're going to add in the force due to gravity, which is negative because it's going down. And that whole thing is going to equal the mass, which of course is 80 kilograms, times the acceleration, which is going to be 0 because it's moving at a constant 3 meters per second. And of course, any time that you're multiplying something by 0, that whole term is going to get to 0. So now we have force normal minus force of gravity equals 0. So rearranging this, we can go now and say that force normal is equal to the force of gravity, albeit in the opposite direction. Taking this one step further, we can go ahead and calculate what the force normal is, which is equal to the force of gravity, and you can calculate the force of gravity, of course, by m times g, where g is the strength of Earth's gravitational field, which is 9.8 newtons per kilogram, and the mass of the little dude is, of course, 80 kilograms. So now we can go ahead and calculate what the force normal is, and the force normal is going to equal, let me get my math right, 784 newtons. So now let's see what will happen if rather than going up at a constant 3 meters per second, we instead accelerate up at 3 meters per second squared. So a lot of this process is going to remain the same. We still have the sum of the forces equals mass times acceleration, and the sum of the forces is going to be force normal, positive since it's going up, and force of gravity, which will be negative because it's going down. Rearranging the algebra a little bit so we can put force normal by itself and add the force of gravity over to the other side, we get mass times acceleration plus the force due to gravity. Now, the force due to gravity, of course, is going to be the mass of the little band times the strength of Earth's gravitational field. So now we can start plugging in numbers. So we have force normal equals the mass of our little dude, 80 kilograms, times the acceleration, which is 3 meters per second squared, going up. So that's going to remain positive. Plus the mass of our little dude again, times the strength of Earth's gravitational field, which is 9.8 newtons per kilogram. Now we have a little bit of a unit mismatch here, but we're okay because kilogram meters per second squared is equal to 1 Newton. So it will all work out in the end. So 80 kilograms times 3 meters per second squared is going to equal 240 newtons. And 80 kilograms times 9.8 newtons per kilogram is going to equal 784 newtons. And when you add both of those up, we end up with a force normal equal to 1024 newtons. So we've seen what happens when our elevator is accelerating up, but unless it belongs to Willy Wonka and his chocolate factory, the elevator is eventually going to have to slow down, which will mean that it will have an acceleration pointing in the down direction. So let's see what this changes in our math. And luckily, it's surprisingly little. So our acceleration is now down, which means that's a negative 3 meters per second, which means we'll have a negative 240 newtons. So that means that the force normal, when the elevator is accelerating down at 3 meters per second, is going to be 544 newtons. So this means that when the elevator is accelerating down, you feel significantly less normal force than when the elevator is either at a constant speed or accelerating upwards. You may notice this when you get into an elevator yourself. When the elevator starts accelerating up, you feel a lot heavier. That's because your normal force is more because you're accelerating up. You can experience the same phenomenon while riding on a swing, a seesaw, or my favorite physics device, the roller coaster.